Ready, sir?
Yeah, I am ready. Yeah. Okay.
Sir, you can start, sir.
So, in the last class we were looking at correlations for heat and mass transfer, and I had discussed first the equivalence of heat and mass transfer. Okay. That is, since the equations are the same, the form of the equations is the same, you just had to replace the energy density by the mass density, energy flux by the mass flux, energy diffusivity by mass diffusivity in order to get the mass transfer correlation. Okay. And because of that, the correlations can be are the same provided the velocity field is the same. That is, the velocity field is specified only by the value of the Reynolds number for that configuration. So, provided the velocity field is the same and provided the properties do not depend upon temperature or concentration. That is, we can consider the diffusion coefficients and the velocity fields to be independent of the mass density or the thermal density, okay, or the energy density. Okay. And we had discussed some more advanced, stronger statements of correlations, in particular the Chilton-Colburn analogy and the Reynolds analogy. And these analogies or equivalences have to be treated with care. One has to ensure that they are applicable in situations that the transport coefficients are all actually constants or close to constants, so that you can consider them as constants while solving the problem. And as far as the analogies are concerned, I told you that the Reynolds analogy is valid only in very specific cases, it is not general, and the Chilton-Colburn analogy also we will see a little later how it arises. Okay. And the other thing that affects these transport coefficients is the flow regime, okay, whether it is a laminar or turbulent flow, the ratio of convection and diffusion through the Peclet number, and surface conditions at the boundaries. Okay. So, using these now we can examine the forms of the correlations in different regimes. Okay. The first regime is what is called the low Peclet number. Okay. For a particle, for example, which has a fluid which is flowing relative to the fluid with some velocity, characteristic velocity v and a diameter d, the Peclet number is equal to v characteristic d by d for mass and the characteristic velocity, the diameter, by alpha for thermal. Okay. If the Peclet number is small, okay, if the Peclet number is small, that means that the transport is primarily due to diffusion. Okay, the transport is primarily due to diffusion. The velocity does not matter. Okay, the velocity is not relevant for this case. Okay, and since the velocity appears in the Reynolds number, right, then the Peclet number, the Reynolds and Peclet number are also not relevant parameters. Okay. And since there are no dimensionless parameters that do not contain velocity, you have to come to the conclusion that the Nusselt number or the Sherwood number are both equal to constants. Okay, in the diffusion dominated regime. Okay, because in the diffusion dominated regime the velocity does not matter, therefore, the Nusselt and the Sherwood numbers have to be constants. Okay. The constant depends of course on the shape of the object, okay, the particular geometry. Okay. For a spherical particle, okay, you can show that the Nusselt or the Sherwood number is equal to 2, in the limit of low Reynolds number. Okay. Okay, for other shaped particles you have to actually calculate the Nusselt or the Sherwood number. Okay. So, those are the correlations in the limit of low Peclet number. Okay. And because the diffusivity is the only parameter in the problem, right, in many cases where the transport is entirely diffusion dominated, you can estimate the time for transport, okay, just based upon the diffusivity and the diameter alone. Okay. So, for example, if I consider, okay, a particle of diameter d that is saturated with water, okay, and it is exposed to air. Okay, so, you wet a particle and you expose it to air, and you can ask what is the time taken for particle for let us say 95% water to evaporate. Okay. So, let us say it takes 10 seconds for 95% of water to evaporate for a 1 millimeter particle. Okay. How much will it take for a 1 centimeter particle? Okay. How do you estimate that? Okay. So, the way to estimate that is to just look at dimensional analysis. The only parameters that are relevant are the diffusivity and the diameter of the particle. Okay. This of course assumes that the rate limiting step in transport is actually the transport of moisture from the surface into the air. Okay. So, if you are drying it in dry air, for example, which has 0 moisture content, the saturation moisture content at the surface is determined entirely by the temperature of the particle. So, if you keep the temperature a constant, the saturation concentration at the surface is the same independent of particle diameter. Okay. So, if that saturation concentration is the same, then the time required for drying can depend only upon the diffusion coefficient and the diameter. Okay. And therefore, the time required from dimensional analysis has to be necessarily of the form d squared by the diffusion coefficient, okay, where d is the mass diffusion coefficient. The mass diffusion coefficient has dimensions of length square per time, okay, and therefore, this gives you a time, and this directly tells you that the time required for drying is going to be proportional to the square of the diameter, okay, provided the drying is of equal extent in both cases. Okay, it is going to be proportional to the square of the diameter. And if you increase the particle size by a factor of 10, then the drying time will increase by a factor of 100. Okay. So, that simple relationship between the drying time can be inferred quite easily just from dimensional analysis in the low Peclet number limit, because the velocity is no longer a parameter. Okay. The only parameter is the diffusion coefficient and the diameter. And all of these, the Nusselt number and the Sherwood number, have all got to tend to constant values in the limit of low Peclet number, because convection is not important. Now, let us look at the other case of high Peclet number. Okay. And in the limit of high Peclet number, of course, there is the distinction between laminar and turbulent flows. Okay, there is a distinction between laminar and turbulent flows, but also there is a distinction between low and high Reynolds number. Okay. Okay. Before I go on to that, I should say that this low Peclet number regime is not really important for flow in conduits. Okay. The reason is as follows. Okay. For flow in a pipe, for example, okay, the Peclet number can be written as V average d by alpha or d. Okay. Okay. Let's just take it for heat transfer. We'll take it as V average d by alpha. okay, where alpha is the thermal diffusivity. Okay. Now, if there is a heat transfer taking place in a pipe, right, of diameter d, okay, okay, the time required for heat or mass diffusion across a distance d, okay, from dimensional analysis has to be equal to d square by alpha. Okay. From dimensional analysis, the diffusion time across a distance d, okay, okay, across the pipe, that is the, if the d is the pipe diameter, the diffusion time across the pipe diameter. Okay. There is the time required for diffusion across the pipe diameter. Okay. Now, what is the distance travelled by the time heat diffuses across the pipe diameter? Okay. So, the distance travelled has to be equal to the diffusion time, that is d square by alpha into VAV. Okay. So, this is the distance that the fluid would travel by the time the temperature has equalized across the entire pipe. Okay. And this distance travelled by the diameter will be equal to VAV d by alpha. Okay. Okay, this distance travelled divided by pipe diameter will be VAV into d by alpha. This is small when Peclet number is small, because this thing is just the Peclet number itself. Okay. This thing is just the Peclet number itself. Okay. So, this is small when the Peclet number is small. Okay. So, basically the temperature is equalized across the entire pipe when the fluid has travelled only a fraction of the diameter. Okay. So, there is no advantage to having a long pipe for heat transfer and trying to pump fluid through it and thereby incurring a high energy cost, okay, for pumping the fluid. Okay. And because of this, the low Peclet number regime is not really of importance in internal flows such as flows through a pipe, because at low Peclet number the heat transfer takes place over a distance that is a fraction of the diameter of the pipe itself. So, there is not much use in having a long pipe for heat or mass transfer in internal flows. Okay. And that is the reason that low Peclet number regime is not really of relevance in internal flows. Okay. Okay. So, now high Peclet number. Okay. You could have two regimes. Okay. One is low Reynolds number, and the other is high Reynolds number. Note that Peclet number is V characteristic length by the diffusion coefficient, okay, and the Reynolds number is V characteristic length divided by the momentum diffusion coefficient. Okay. This is the mass or heat diffusion coefficient, okay, either the mass diffusion coefficient or the heat diffusion coefficient, and the Reynolds number is the same parameter with the momentum diffusion coefficient substituted for the mass or heat diffusion coefficient. Okay. When we discuss diffusion next, we will see that the mass, heat and momentum diffusivities in gases are all approximately the same. Okay. They are all comparable to each other. Okay. And therefore, if the Peclet number is large, the Reynolds number will also be large. Okay. So, in case of gases at high Peclet number, invariably the Reynolds number will also be high, because the mass, heat and momentum diffusivities are comparable in gases. Okay. On the other hand, in liquids we will see that the mass diffusion coefficient, okay, the mass diffusion coefficient is actually much smaller than the momentum diffusion coefficient, okay, for mass transfer. Okay. Okay. Similarly, in liquids the thermal diffusion coefficient could be either smaller or it could be much larger than the momentum diffusion coefficient. Okay. We will see this next when we actually estimate the diffusion coefficients, right. That means in liquids, because the mass diffusion coefficient is much smaller than the momentum diffusion coefficient, you could have simultaneously a regime where the Peckley number is large and the Reynolds number is small. Okay. You could simultaneously have a regime because the mass diffusion coefficient is much smaller than the momentum diffusion coefficient. You could have a regime where simultaneously the Peckley number is large and the Reynolds number is small. Okay. So, even in the case of heat transfer in liquids where the thermal diffusion coefficient is much smaller than the momentum diffusion coefficient, you could have this regime. Okay. What that means is that convection is large compared to diffusion as far as the mass or heat transfer is concerned, but viscous effects are dominant compared to inertial effects in momentum transfer. Okay. So, this this happens, for example, okay, in the flow past a particle, for example. This would happen, we saw earlier, when the Reynolds number is less than about 1.5. Okay. There is symmetry between the upstream and the downstream sides, okay, of the flow past a particle, okay, and the velocity profile is symmetric. And similarly, in a pipe it happens, okay, at low Reynolds number below the transition between laminar and turbulent flow. The velocity profile is what is called a parabolic profile. Okay. And in the limit of low Reynolds number, when the Reynolds number is small, okay, the problem is what is called linear. Okay. And that is that in the pipe, for example, if I were to increase the pressure drop for a laminar flow, the velocity would increase. Okay. The velocity would increase, it would go to a higher value, okay, but it would still be parabolic. Okay. It would still be parabolic. In other words, the form of the velocity will be exactly the same, even though the form of the velocity profile will be exactly the same, even though the velocity itself has increased. Okay. So, for example, if you divide the velocity at any point by the maximum velocity, it is going to be the same, okay, at each point within the pipe. So, if I take a particular location, okay, if I take a particular location in the pipe and I divide the velocity at that location by the total velocity, that ratio will be the same. Okay, it will be independent of the flow velocity. Okay. Similarly, for the flow around a particle, if I take the velocity at any point, okay, within the flow and I divide it by the free stream velocity, that ratio will be the same as the velocity is increased. Okay. So, as I keep increasing the free stream velocity, the velocity at every point around the particle increases. However, the ratio of the velocity at some point within the fluid divided by the free stream velocity remains the same. Okay. In other words, the form of the velocity profile is unchanged even though the velocity changes. Okay. And because the form of the flow pattern is unchanged as the velocity increases, the effect of convection can be represented by only one characteristic velocity. Okay. The nature of the velocity profile remains the same as the Reynolds number increases, which means that one characteristic velocity can be used to represent, okay, the strength of convection. And if you define the Peckley number with respect to that velocity, then the transport coefficients should depend only upon that Peckley number because of linearity. Okay. So, therefore, the in this limit, okay, so the Nusselt number and the Schmidt number will be only function of the Peclet number, okay, because all of the information regarding convection is encapsulated in this one velocity, because the velocity profile is not changing even though the magnitude of the velocity is changing. So, if I define the Peclet number either with respect to the free stream velocity or the average velocity, because the velocity at every point in the fluid is proportional to these quantities. Okay. Therefore, the correlations will depend only upon the Peclet number, they will not depend upon the Reynolds number, okay, in this limit where the Peclet number is large and the Reynolds number is small. Okay. On the other hand, if I go to the case where the Peclet number is large and the Reynolds number is also large, okay, in that case, as we saw, the flow pattern does change as the Reynolds number changes. Okay. For the flow past a particle, between about Reynolds number of 1.5 to 24, there was asymmetry between the front and the rear halves. 24 to 400, there was a separation bubble, okay, and so on. Okay. So, there is steady progression in patterns. So, the velocity pattern is changing, and because of that, the Nusselt number and the Sherwood number will be equal to functions of the Reynolds number and the Peclet number. Okay. Okay. Reynolds number and the Peclet number, because the Reynolds number, the velocity pattern, okay, the velocity profile changes with Reynolds number. Okay. For the flow in a pipe, since the flow is parabolic up to the laminar turbulent transition, the Nusselt and Schmidt numbers will be a function of the Peclet number up to transition, okay, because the velocity profile is parabolic all the way up to transition. And after transition it becomes turbulent, and in a turbulent flow, of course, okay, the Nusselt and the Schmidt number will be equal to the function of Reynolds number and the Peclet number. Okay. I have written these in terms of the Reynolds number and the Peclet number. You could write these in terms of Reynolds number and Prandtl number using the substitution Peclet number is equal to Reynolds number times Prandtl number. Okay. So, that is a straightforward extension. Okay. Okay. So, with this basic background on the nature of the correlations, let us look at correlations for some specific cases. Okay. First, I will consider flow in a pipe. Okay. And I will give you the Nusselt number correlation in this case. The Prandtl number correlation, sorry, the Sherwood number correlation can be derived by just substituting for the mass Peclet number for the heat Peclet number, okay, in the correlation. Okay. For a laminar flow, if we consider a pipe with diameter d and length L, okay, if we consider a pipe with diameter d and length L, for a laminar flow, the Nusselt number is given by the correlation 1.86, okay, Peclet number per 1/3 d by L per 1/3. Okay. Okay. It is commonly written as 1.86 Re per 1/3 PR per 1/3 d by L per 1/3. Okay. And so, this depends upon the length to diameter ratio as well as the Reynolds number and the Prandtl number. And in the case of heat transfer, there is often a correction factor for the viscosity added, mu by mu w per 0.14. Okay. Okay, 0.14, where mu is the viscosity of the fluid at the average temperature of the fluid, mu W is the viscosity of the fluid at the temperature of the wall. Okay. So, in cases where the viscosity varies with temperature, you have to include a correction factor, okay, because of the variation in viscosity, and that correction factor is usually included as mu by mu W power 0.14. Okay. So, this is the correlation for a laminar flow. We will examine this correlation later on, and we will show that this entire correlation, the form of the correlation with the exception of the prefactor, can actually be derived, okay, using what is called boundary layer analysis later in the course. Okay. So, up to that point we can derive it using what is called boundary layer analysis. Okay. And this 1/3 power also we will examine why there is a 1/3 power. As I said, this is applicable for Peclet number large compared to 1 laminar flow. I told you that the Peclet number small compared to 1 regime is not actually relevant for the flow in a pipe. Okay. For a turbulent flow, you have a similar correlation. Okay. Nusselt number is equal to 0.023 Re per 0.18 sorry PR per 1/3 and mu by mu W per 1/3. Okay, this is the correlation for a turbulent flow in a pipe. Okay. And this correlation cannot be derived from first principles. Okay, we will see that later. Okay. This is an empirical correlation and has to be considered as such. Okay, so, this gives you the correlation for heat or mass transfer for the flow in a pipe in the limit of Peclet number becoming large. There are limitations on this correlation. So, this correlation is valid only for a laminar flow, and it is also valid only when d by L is below a threshold. Okay. We will come back and examine why that threshold requirement arises. Okay. Only for d by L that is below a threshold, which is variously described as 10,000 or 20,000, only then is this correlation valid. Okay. And the other assumption here is that the flow is fully developed right from the entrance. That is not strictly true, okay, because there is some development length at the entrance of the pipe beyond which only these correlations are valid. Okay. So, in both cases the dependence on Prandtl number is the same. The dependence on Reynolds number changes. For a laminar flow, we know that it has to depend only on the Peclet number, because the evolution of the velocity profile has the self similar form. Okay. You have the same profile, and because of that it can depend only on the Peclet number. For a turbulent flow, there is no such requirement, and therefore the velocity field has different the Reynolds number dependence is different in this case. Okay. So, the correlation for mass transfer will be the same, except that you will not have this mu by mu W power 1/3 in the correlation. Okay. That is because we assume that the diffusion coefficient does not depend on concentration. Okay. So, the diffusion from the wall of the pipe, the problem of the mass transfer will be exactly the same correlation, except that this correction for viscosity is not present. Okay. So, we will I have so far discussed with you what are the high Peclet number limit, the low Peclet number limit where the Nusselt and Sherwood numbers are a constant. High Peclet number, if the Reynolds number is low, the Nusselt and Sherwood numbers depend only on the Peclet number, and if the Reynolds number is high, they depend on the Reynolds number and the Peclet number. Okay, and I had given you the correlations for a pipe. Okay. So, we will solve an example of the rate of heat transfer in a pipe using this correlation, and then we will proceed to looking at heat and mass transfer for a flat plate, and later on for the flow around a particle. Okay. So, we will continue this in the next lecture. I will see you then.